What if I told you that light can make things move?
No, not like that. The pushing force of light is actually very, very small, but the sun produces so much of it that we can use it to push space travel farther than it's ever been. Over 400 years ago, Johannes Kepler observed that the tails of comets were always pointed away from the sun. He postulated that the sun produced a certain pressure that did this. A few hundred years later, this pressure was proven to be exerted by sunlight, based on which the idea of the solar sail was born. A solar sail harnesses the pushing power of light to move through space, similar to how wind pushes sailboats. In 2010, Japan demonstrated solar sail technology in interplanetary space successfully for the first time. Most recently, the US-based Planetary Society launched the LightSail 2 atop SpaceX's Falcon Heavy rocket in 2019. So how exactly can light push things? To answer that, we have to understand two concepts. First, how a moving object moves another object, and second, what light really is. In physics, an object making another object move is explained as a transfer of momentum. Momentum can be understood as mass in motion. If I kick this ball, the ball now has momentum. And if it then hits another ball, it imparts that momentum onto the second ball and makes it move. Light, when reduced to its smallest unit, is made up of photons, which can be understood as tiny bundles of energy with no mass, and obviously travel at the speed of light. It's these photons that hit the sail and transfer their momentum to it.
Wait, but if momentum is mass in motion and photons are massless, how can a photon have momentum? It's because they travel so fast. At the speed of light, they are no longer governed by the laws of Newtonian physics. This is where Einstein's theory of special relativity comes in, stating that energy, mass, and momentum are all related. As per the energy-momentum relation, given photons have no mass, the momentum of a photon is P equals E over C. Now, this is the formula for the velocity of a solar sail. The reason there's a 2 here is because a photon transfers its momentum of E over C when it hits the sail, and another E over C when it bounces off. So the total momentum gained is 2 E over C per photon. Based on this equation, we can improve a solar sail by gaining higher intensity of incoming light, building a sail with larger area, optimizing reflectivity, and reducing the mass. Now let's take a look at the most recent solar sail. It is 32 square meters of a plastic film with a reflective metal coating that acts like a mirror. It is also extremely thin, being only 4.5 microns thick. With these parameters, we can predict LightSail 2's speed. After 1 day of operation, the sail would reach a speed of 5 meters per second, and after 50 days, its speed will reach 250 meters per second. The beauty of a solar sail is that it will continue to accelerate as long as there is sufficient light. Unlike a rocket, it requires no fuel and is less expensive.
So where does this lead us? The applications could include inexpensive shuttling between Earth and Mars, or can also be as ambitious as interstellar travel, with the potential to reach our nearest star system, Alpha Centauri.